in HASBOT. I'll go ahead and open up a preview version. You should go to learn.concord.org and sign in. If you're not signed into Rapid Identity, make sure you do. If it says anonymous in the upper right, it should not. It should say your name. If you'd like to tap to listen, that allows the text to be read to you. I'm going to go ahead and go to Activity 3, Moving Stars and Their Planets. All right, the first page is just a description as to what you're going to be learning. It says it's going to take you 60 minutes to complete. It should not take you that long, but if it does, that's okay. You've got time to complete it. I'm going to click Begin Activity, and the first one talks about having a ball, if you're swinging a ball around you, okay? And then we're going to show you the effect that it has on a star. So I'm going to click Play here. And we can change the planet type. This is showing a planet orbiting a star. And you can change the planet diameter if you want to see what effect it has on the star. Hopefully you remember from our slideshow, Wibbly Wobbly Planets, what's going on here. Okay, so manipulating that, you'll answer these questions. And then you're going to make a claim. What happens to the wobble motion of a star when a planet has a very low mass? When you're done, go to the next page. Next is the Doppler effect. Studying the Doppler effect, you're going to take a look at how light reacts when a star is moving toward or away. So if I move this toward or away from the telescope, you can see what happens to the wavelengths of light. And if we take a look, I'll just pause it. If you take a look at the graph, you can also see the velocity when you're moving it. When you're moving it away from the telescope, it has positive velocity, and when you're moving it toward the telescope, it goes to negative velocity. It says to take a snapshot that shows both long and short wavelengths. If you don't know how to do that, I'll do that real quickly for you. Okay, I'm showing long wavelengths, short wavelengths, and I'll click pause. So practice that, and then you can take a snapshot by clicking Take a Snapshot, answer the questions, and move on to the next one. Next, how is the star moving? It says, a scientist observes that the light from a star seems to be yellow in the visible portion of the spectrum. Based on the observations, can the scientist be certain that the star is not moving? All right, how certain and so on. Explain your rating. Next. The importance of angle. So in the video you saw at the beginning of this unit, you saw that there are two ways that scientists use light to look for planets: the wobble method, which is Doppler technique, and the transit method. We've learned about both of those now. Now this is going to help you understand how angle affects the velocity of a star relative to the observer. So we're looking for that Doppler shift again. And if I go ahead and press play, you'll see the star moving. And what I can do is I can click with one finger and then move, and I can change the angle. Okay. So it's completely in line with you, or it's completely at a 90-degree angle. The degrees are shown down here. Knowing how to do that, answer the questions. How certain are you, and so on. Okay. Ready to move on to the next one when you're done filling those in. Page 5 is the absence of wavelength shifts. So scientists look for planets by studying the light from a newly discovered star. The velocity graph of the star's motion indicates no motion of the star toward or away. The scientist decides the star doesn't have planets. Do you agree with the scientists? And go ahead and answer the questions. Next is the importance of mass. The mass of a planet plays a crucial role in how much the star will move. The angle at which the planet orbits its star affects our abilities to detect it. So the combination of planetary mass and orbital angle affects the shape of the velocity graph. So the challenge is to set up the model with a very large mass, so a very heavy planet, that results in a similar velocity graph to this one. Okay, now it can be close. You're not going to get it perfect. So it says you can use the zoom button on the graph to see very small movements of the star. So we want to set something with a very large mass. So you're going to play with it at the bottom, planet diameter. You want something very large. Okay, I'm going to press play. Now, nothing's happening here because there's no motion toward or away. If I tilt it just a little bit, okay, now I can see just a small motion up and down. That's pretty good, pretty close to that. You might want to play around with that. It says take a snapshot that shows a very large, very heavy planet that has between a -0.2 and 0.2 meters per second. I'm not going to worry too much about that. If you get kind of a pretty gentle slope here, you'll be fine. The point is that you can have something, because of the tilt, even though something's very massive, not moving the line very much at all. Okay. Then answer the questions. It says a velocity graph was recorded by pointing a telescope at a nearby star. The scientist determines that the star must have a very large planet orbiting around it. You agree? And explain your answer. Next. This one has to do with noise. So the telescopes in previous activities were like perfect. Okay. We don't get that in real life. So here's a perfect telescope. More realistic data is like this fuzziness. So you're given this. Does this show a planet orbiting a star? What do you think? And what more information would you want to be sure of your answer? Question or page 8. Finding planets through the noise. You're going to explore the orbital effect, the orbital angle with noise. So it says position, let me get rid of this. Position the orbital angle of the planet so it's close to but not exactly 90 degrees. So currently it's 90 degrees. I just tipped it a little bit, 83 or whatever. Make a planet that you can just detect on the velocity graph without using the zoom button. So I'm going to press play. So how would I make one that I can just detect? Now I'm looking at the graph. Does it appear to go up and down? I really can't see it, but I'm going to go ahead and move to, I'll go a gaseous planet, and I'll go a whole lot to Earth. I cranked up the size, and you can see that you can just detect it. You can play around with that to determine how much you want to do there. It says most of the planets that have been discovered orbit their stars at a tilt closer to 0 degrees than 90 degrees. Why do you think it's true? Why are we discovering more planets with a tilt closer to 0 degrees than that of 90 degrees? And why might a scientist using modern telescopes be unsure about having discovered a planet? I think they're relating that to the amount of noise, or possibly that the planet might not be in a perfect position. And finally, the last page is finding planets through the noise, and we're focusing on mass with this one. Set the telescope precision slider to its perfect setting of 100. So we're going down here. We're setting this slider to 100%. It is already there as the default. Make a planet with a small mass. It already has a small mass. Select an orbital angle that allows you to detect the planet, and then change the precision of the telescope to explore how varying levels of noise affect your ability to detect the planet. So I'm going to go ahead and press play. And I'm going to play around with this, and we're going to get it so we can detect the planet. Now, I talked earlier about using the zoom button. I'm going to go ahead and click the zoom button. You can see it there. Okay, I'm going to get rid of a little bit here, move the angle, Let's let this come back. Move it. I'll clear the graph and start over. All right, this is a little bit better. And as I change the tilt, you can see how it affects the graph there. I'm going to move it back. I'm going to zoom in again, clear the graph, zoom. That's really zooming a lot to 3 meters. It'll stabilize after it runs a little bit of the data here. So I'm going to let that go. All right. Now you're going to change the telescope precision. I'm going to make this go faster just to kind of get it moving a little bit. As you change the precision, you'll see, let me get rid of the zoom, clear the graph. I'll speed it up. All right, so as you change the precision, you see it's kind of hard to see the graph moving as much. I'll increase the size of it just a little bit, see if I can get a little bit of a movement. There we go, that's a little bit better. Play around with it. Question: most of the planets that have been found so far have been very massive. Why? Now, as you take a look at this velocity graph, could there be a planet? Explain your answer, and then you're done. That will complete the activity. Go ahead and have this done. We will continue with this Thursday. Tomorrow, Wednesday, we will do our a different simulation. So work on this today.